Hello, and welcome to Space for Sleep. I'm so glad you're here. Whether you're settling into bed, curling up on the couch, or simply giving your mind a quiet space to wander, you've come to the right corner of the cosmos. This is where science slows down just enough for you to feel it, where the vast universe becomes small enough to fit inside your imagination. Tonight, we're traveling not through space, but through time itself. Time, that invisible current that carries everything forward, from the birth of the stars to the flicker of a thought inside your mind. But what if that current could be reversed? What if you could step outside the flow, walk upstream, and visit yesterday as if it were just another country on the map of the universe? It sounds impossible, like something out of science fiction, but physicists don't see it as pure fantasy. For more than a century, the world's greatest minds have quietly wrestled with one question: is time travel physically possible? Before we dive deep into the equations, paradoxes, and possibilities, take a moment to like this video and subscribe to Space for Sleep, your gateway to the universe's most fascinating mysteries. It helps this channel grow and keeps this journey alive. Now, close your eyes for a second. Imagine standing at the edge of space-time, the invisible fabric that weaves together every second and every star. What if I told you that the future and the past might already exist, waiting for you, like pages in a cosmic book, and that the only thing stopping you from flipping backward is the way you're built to experience reality? Einstein once said that the distinction between past, present, and future is only a stubborn illusion. But if it's an illusion, can we break it? Can we engineer a way to slip between those pages, not in imagination but in physics? To answer that, we'll start at the beginning, with time itself. What is it? Where does it come from? And could it, under the right conditions, be bent, stretched, or even folded back upon itself? Let's begin. Before we can dream about traveling through time, we have to ask a deceptively simple question: what is time? We feel it pass, but we can't hold it. We measure it, yet it has no texture, no color, no sound. We live our entire lives inside it, and still, no one truly knows what it is. For most of human history, we thought of time as something absolute, ticking away the same everywhere, a steady rhythm like the beating of a perfect cosmic clock. But that picture shattered in 1905, when a young patent clerk named Albert Einstein looked at the universe and saw something completely different. Einstein's special theory of relativity told us that time is not separate from space. Instead, they're part of a single fabric, space-time. Move through space, and you move through time. The faster you move through space, the slower you move through time. That means your time, my time, and the time experienced by a particle racing near the speed of light are not the same. It's strange, isn't it? Imagine you and I are twins. You stay here on Earth, and I board a ship that can fly close to the speed of light. I travel for what feels like a few years, then turn around and come home. But when I land, you're decades older. I've only lived a few years, but you've lived a lifetime. That's not science fiction, that's physics. We call it time dilation. Time slows down for anything moving at extreme speeds or sitting in a powerful gravitational field. This means, in a way, time travel to the future is already real. Astronauts aboard the International Space Station experience it right now, though the difference is measured in mere milliseconds. Still, that tiny effect is proof. Proof that time isn't fixed, proof that it bends. If time can bend, could it ever bend back on itself? Could you travel not just forward, but backward, to moments that have already happened? That's where the real paradox begins. But before we fall into the rabbit hole of paradoxes, let's stay here for a moment and breathe in the wonder of what we already know. Every second you experience, every heartbeat, every movement of the stars, all of it is stitched together by this invisible cosmic fabric. Time isn't a line on a ruler. It's a living geometry, molded by motion and gravity. If you're enjoying this quiet journey through space-time, remember to like this video and subscribe. It helps this channel bring science to life in a way that feels human, warm, and alive. Now, imagine standing near something massive, say a black hole. The gravity is so strong that time itself slows to almost nothing. A minute near the event horizon could be years for someone far away. You could look out and watch the universe race forward, a kind of natural time machine. But to understand how far that idea can go, we'll need to explore not just relativity, but the very limits of cause and effect, and the strange possibilities that arise when space twists so much that time no longer knows which way to flow. So, take a deep breath. In the next part of our journey, we'll step closer to the edge of the possible, where gravity, quantum mechanics, and imagination meet, and ask what would really happen if you tried to travel back in time. Let's go deeper. Imagine the fabric of space-time as a vast ocean. Normally, we drift gently forward, 1 second at a time, carried by the steady current we call now. But under extreme conditions, immense gravity, staggering energy, or extraordinary speed, those currents twist and curl, forming eddies and loops. Some physicists believe these loops could, in theory, allow time to fold back on itself. This idea has a name, a closed, time-like curve. It's the scientific term for what we might casually call a time loop. The mathematics of general relativity, Einstein's great masterpiece, doesn't forbid such curves. In fact, under certain conditions, the equations predict them. So, could the universe itself be hiding tiny doorways through time? One of the most famous possibilities involves wormholes, hypothetical tunnels connecting 2 points in space-time. If a wormhole could somehow be stabilized and manipulated, it might allow a traveler to enter one mouth and exit the other at an earlier or later time. Theoretically, you could leave today and arrive yesterday. But there's a problem. Wormholes, as far as we know, are incredibly unstable. The moment they form, they want to collapse. To keep them open, you'd need something exotic, matter with negative energy density. We've never found such material in the lab, but quantum physics suggests it might exist in minute quantities in the vacuum of space. If it does, then perhaps, just perhaps, the key to time travel isn't hidden in massive machines or starships, but in the shimmering quantum foam that underlies all of reality. Pause for a moment and imagine this. Beneath the surface of what looks like empty space, the quantum world flickers with constant creation and destruction. Particles appear and vanish faster than thought. Tiny wormholes might pop in and out of existence, far too small for anything macroscopic to pass through, but they're all the same. A seething sea of potential time tunnels, invisible to us. This isn't fantasy. It's quantum mechanics. Strange, unpredictable, and deeply real. Now, here's where things get fascinating. If you could somehow stretch one of those microscopic wormholes to macroscopic size, stabilize it with exotic matter, and move one end at high speed, time dilation would kick in. The moving end would experience time more slowly than the stationary one. When you brought them back together, you'd have a bridge between two different moments in time. Step through, and you step backward. It sounds absurd, but the math works. It's not that physics forbids time travel. It's that nature might simply make it unbelievably difficult. And yet, there's another layer. Even if you could create a time machine, would the universe let you use it? This brings us to the most famous problem in all of temporal physics, the grandfather paradox. Suppose you travel back in time and prevent your grandfather from meeting your grandmother. If he never has children, your parents are never born, and neither are you. But if you're never born, how could you have gone back to stop him? The paradox folds in on itself, an impossible loop. It's the ultimate contradiction. Some physicists suggest that the universe simply doesn't allow paradoxes. They say something, perhaps a quantum rule or a hidden law, would always conspire to prevent them. This is known as the Novikov self-consistency principle. It means that whatever you do in the past was always part of history. You can travel back, but you can't change anything that would make your journey impossible. In other words, time protects itself. But others disagree. They believe in a multiverse, countless parallel timelines branching like the veins of a leaf. Change something in the past, and you don't erase your own timeline. You simply create a new one. In that new branch, your grandfather never met your grandmother, but your original world still exists, untouched. In that sense, time travel wouldn't rewrite reality. It would split it. Imagine, for a moment, the emotional weight of that. Traveling back in time to save someone, to undo a tragedy, only to realize you've created a new reality where they live, while the one you came from remains frozen in loss. You would remember both worlds, but you could never return to the one you left. It's beautiful. And haunting. Before we move further, take a breath. Let this sink in, because as abstract as it sounds, this is the real frontier of modern physics. Not fantasy, not fiction, just the strange, unavoidable consequences of what happens when you take Einstein's equations seriously. And if you're enjoying this deep journey through time and space, don't forget to like this video and subscribe to Quantum. It helps us keep exploring the universe's biggest questions, quietly, curiously, and together. In the next section, we'll go deeper into the paradoxes, exploring what quantum mechanics has to say about causality, probability, and the mysterious possibility that the universe might already contain hints of its own future. Let's step forward, or perhaps backward, and see what time has in store. Let's imagine, for a moment, that you could actually watch the flow of time itself, not through a clock or a calendar, but as a vast, living landscape, a dimension as real as space. You would see everything that has ever happened, and everything that ever will happen laid out before you, like the grooves on a vinyl record. You wouldn't move through time. You would simply move your point of awareness along it. This is the concept of the block universe, one of the most fascinating and unsettling ideas in modern physics. According to this view, past, present, and future all exist simultaneously. The universe isn't becoming, it simply is. You, right now, are just one slice of a much larger cosmic structure that already contains your entire life. Every memory, every heartbeat, every possibility. If that's true, then the future isn't waiting to be written. It's already there. Time travel, in that sense, wouldn't be about changing anything. It would simply be about visiting another coordinate in space-time. But here's the catch. While relativity paints this beautiful geometric picture of time, quantum mechanics doesn't play along so easily. Quantum physics lives in the realm of probabilities, not certainties. In the quantum world, particles don't have definite positions or states until they're observed. They exist in a haze of possibilities, a cloud of maybes. This is where things get strange. If the universe at its core is quantum, and the future isn't yet determined, then how can it already exist in the block universe? Does time, at the smallest scale, flicker into being as we observe it, moment by moment, like frames in a cosmic film strip? Or are all those frames already there, waiting for consciousness to illuminate them one by one? No one knows for sure, but these questions are leading physicists into new territory, where the nature of time, reality, and consciousness seem to overlap. Imagine for a second that you had the ability to move your consciousness to any point in that film strip, any now in the entire timeline of your life. Would that count as time travel? Physically, your body wouldn't move, but your awareness would shift to another point in space-time. To you, it would feel real. And maybe, just maybe, that's what déjà vu really is, a brief, flickering echo of another frame in the reel. Einstein once wrote to the family of a close friend who had died, for us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. That line still resonates because it suggests something quietly revolutionary, that death, loss, and the passage of time might not erase anything. Everything we love, everything we are, might still exist, eternally recorded in space-time. But science doesn't stop at comfort, it asks hard questions. If time is already written, then why does it feel like it's moving? Why do we experience change, growth, and aging? The answer may lie in something called entropy, the tendency of the universe to move from order toward disorder. Entropy gives direction to time. It's why you can mix cream into coffee, but never unmix it. Why you remember the past but not the future. Entropy is the arrow of time, the one-way street that keeps us moving forward. Even if time itself is a dimension that exists all at once, entropy forces us to experience it sequentially. Without it, time would be meaningless. Every moment would be frozen, like an unplayed note in a song. So perhaps time travel isn't impossible. It's just that our minds, bound by entropy and biology, can only move forward. Still, the dream persists. What if we could break free from that arrow? What if we could find a way to travel against the current, back to a previous configuration of the universe, or forward to a version that doesn't yet exist? To answer that, we have to go smaller, to the realm of subatomic particles where the usual rules break down and cause and effect start to blur. At this scale, time doesn't always move in one direction. Some equations of quantum physics are perfectly symmetrical, meaning they work the same whether time flows forward or backward. To the math, the universe doesn't care which way the arrow points. This opens a fascinating possibility. Perhaps time isn't fundamental at all. Maybe it's something that emerges from deeper, timeless laws of physics, just like temperature emerges from the motion of molecules. If time can emerge, then maybe it can unemerge under the right conditions. And that might be the key to unlocking time travel. Take a slow breath. Let that thought linger. The very thing you take for granted, the passing of time, may not be a basic part of reality. It might be an illusion created by how we, as conscious beings, interact with the universe. In that sense, time travel could be less about building machines and more about understanding perception. Maybe to move through time, you don't need to bend space-time. You need to bend awareness. Before we dive into that extraordinary idea, take a moment to like this video and subscribe to Quantum. It helps keep this quiet journey through science alive, where curiosity meets calm and physics meets wonder. In the next section, we'll go further into quantum time, exploring particles that seem to defy causality and experiments that suggest the future might influence the past. Because if that's true, then maybe, just maybe, time travel has already happened. Picture the quantum world again, that invisible stage where particles blink in and out of existence faster than thought. Down here, cause and effect are no longer solid walls, they're soft ripples. And sometimes, those ripples move in both directions. In 2017, a small group of physicists ran a thought experiment that stunned the community. They asked, what if a particle could send information backward in time? Their math said it wasn't strictly forbidden. In certain quantum systems, the future could, in theory, affect the present. That means decisions not yet made could shape outcomes already happening. It sounds impossible until you realize that quantum mechanics already hints at this. In the famous double-slit experiment, a single electron seems to pass through two openings at once, until you look. The moment you observe it, its wave of possibilities collapses into one outcome. Observation changes reality. But when, exactly, does that change happen? Some interpretations suggest the act of measurement reaches backward in time, reshaping the particle's history to fit the result you just saw. If that's true, then the boundary between before and after might be far thinner than we imagine. Let's pause here. Think of your life as a vast quantum pattern, every choice a ripple spreading through the possibilities of the future. What if, somewhere deep in that pattern, the future also whispers back? Maybe intuition, that sudden flash of knowing, is the faint echo of information leaking backward through time. We don't yet have the instruments to prove it. But physics keeps nudging us toward that eerie idea that time, at its core, isn't a straight arrow at all. It's a network, a web, maybe even a loop. Now let's climb out of the microscopic world and back into the cosmic scale, because if quantum particles can play with causality, perhaps the universe itself can too. In 1949, a brilliant mathematician named Kurt Gödel discovered something astonishing hidden inside Einstein's own equations. He found a model of the universe that could rotate. In this rotating cosmos, the geometry of spacetime allowed paths that curved back onto themselves, meaning you could, in principle, travel into your own past. Einstein didn't reject Gödel's math. He simply called it too strange to describe reality, but mathematically it worked. If the universe had the right kind of spin, time travel was embedded in its structure. No one thinks our real universe is rotating that way, but Gödel proved an important point. General relativity doesn't ban time travel, it just hides it behind impossible engineering. Still, we've learned to be careful with the word impossible. A century ago, so was heavier than air flight. So was splitting the atom. So was talking to someone on the other side of the planet through a handheld piece of glass. Physics tends to yield to curiosity, slowly, stubbornly, but inevitably. Now imagine a far future civilization that has learned to manipulate space-time itself, not just travel through it, but sculpt it, bend it the way we bend light through glass, with enough energy, perhaps even create a region where time's arrow reverses. To us, it would look like a miracle. To them, it would just be advanced geometry. But here's the haunting part. If such civilizations ever existed, would we even notice them? A time traveler who stepped out of a reversed region might appear frozen, ghost-like, or invisible. We'd call it a glitch in reality, when in fact it was someone moving through a different slice of space-time. There's a quiet possibility whispered among some cosmologists that what we call dark energy, the mysterious force accelerating the expansion of the universe, might be related to time itself stretching unevenly. Maybe dark energy is a kind of temporal pressure, pushing moments apart faster and faster. If so, controlling it might one day allow us not only to expand space, but to navigate time. Take a slow breath. Feel the enormity of that idea settle. Because if that's even partly true, time travel isn't about building a machine. It's about understanding the deep geometry of reality, the way energy, gravity, and quantum information weave together to create the illusion of flow. Before we drift further, a gentle reminder, if you're enjoying this exploration, tap like and subscribe to Quantum. It's a small gesture that helps keep these journeys alive, quiet, thoughtful, and infinite. Now, in the next part of our journey, we'll step into the strangest realm of all, the quantum gravity frontier, where black holes, information, and time become inseparable, and where the line between forward and backward might vanish completely. Close your eyes and picture a black hole, a silent sphere of darkness hanging in space. Nothing escapes it, not even light. To us, it looks like an end, a place where time itself stops. But to a physicist, a black hole is a laboratory, the ultimate experiment written directly into the sky. At the heart of a black hole lies the point we call the singularity, a region where our equations collapse and space and time lose meaning. The closer you get, the slower time runs. To a distant observer, anything falling toward the horizon seems to freeze, trapped forever at the edge. But to the falling traveler, time keeps flowing normally. They cross the horizon without noticing, carried inward toward a region where the known laws of physics dissolve. Here, time and space switch roles. Inside the horizon, moving forward in time means moving deeper toward the singularity. There's no choice, no escape, only the inevitable march inward. And yet, according to general relativity, there might be other kinds of black holes, spinning ones, charged ones, whose geometry could connect different regions of space-time. Some of these theoretical solutions look like tunnels, Einstein-Rosen bridges. To us, they're wormholes. If such a bridge could exist, it might link not just distant places, but distant times. Step through one mouth and emerge centuries earlier or later. But to keep that passage open, you'd need negative energy, the same exotic substance that appeared earlier in our story. Without it, the tunnel collapses in an instant, sealing both ends forever. Stephen Hawking once proposed the chronology protection conjecture, the idea that nature itself forbids time machines. Quantum effects, he argued, would flood any attempted time tunnel with radiation and destroy it before paradoxes could arise. In his words, the laws of physics conspire to prevent time travel on a macroscopic scale. It's as if the universe protects its own timeline the way a body protects a wound. Still, other physicists wonder whether small quantum-scale violations of chronology might occur all the time, harmlessly. Particles might borrow bits of energy, loop through tiny intervals of space-time, and return before they're missed, microscopic time travelers flickering everywhere, unseen. To test ideas like this, researchers turn to mathematics and to quantum field theory, trying to understand how information behaves near black holes. When something falls in, does its information vanish, or does it get encoded somehow in the radiation that escapes, the mysterious Hawking radiation? If information can never truly be destroyed, as quantum mechanics insists, then black holes may be cosmic archivists, preserving every detail of history in subtle quantum imprints. That thought leads to something profound. Maybe time isn't lost inside a black hole at all. Maybe every event that ever fell in still exists there, written on the horizon, waiting to be read in a future so far ahead we can barely imagine it. If we could decode that cosmic library, we wouldn't need to travel back in time. We'd simply see the past, perfectly preserved in the fabric of the universe itself. Now think about this. When we look into the night sky, we're already seeing the past. Light from distant galaxies takes millions or billions of years to reach us. Every star you see is an ancient photograph, a time capsule sent long before humanity existed. In a sense, your eyes are tiny time machines, catching photons that began their journey before Earth had continents. The deeper we look, the further back we go, until we reach the cosmic microwave background, the afterglow of the Big Bang itself. That faint radiation still whispering across the cosmos is the oldest light we can see. The universe has already given us a way to witness its own history. We just had to learn how to listen. So, perhaps the first step toward time travel isn't to move ourselves through time, but to learn to read the signals time leaves behind. Maybe the universe is constantly showing us where it's been. We just haven't yet learned how to interpret every echo. Take a breath. Feel the quiet enormity of that idea. Each photon of light that reaches you carries a story billions of years old. When you hold your hand out under starlight, you are literally touching the past. Before we continue, if this journey through the physics of time resonates with you, take a second to like this video and subscribe to Quantum. It's a small act that keeps this space alive, where curiosity meets calm and wonder has time to breathe. In the next section, we'll step beyond black holes to the beginning itself, the instant of the Big Bang, and ask the boldest question of all. If time began there, could it also end and begin again? Imagine rewinding the universe. Galaxies contract, stars unform, light blue shifts into brilliance. Every atom, every particle, every wisp of radiation collapses inward until everything, all of space, all of time, is compressed into a single, unimaginable point. This is the Big Bang singularity, the moment time itself is thought to have begun. But what does it mean for time to begin? If we travel backward through history, counting seconds, minutes, and eons, we reach a boundary where the very concept of before no longer applies. Time isn't just empty space waiting to be filled. It's part of the fabric that came into existence with the universe. Before the Big Bang, there was no before. The question, what happened before time began, might not even make sense. It's like asking what's north of the North Pole. Still, physicists can't resist trying to peek past that boundary. Quantum cosmology suggests that on unimaginably small scales, space-time behaves like a restless ocean of possibilities. The early universe may have flickered into existence through quantum fluctuations, spontaneous moments where the vacuum briefly births a universe, a bubble of space-time expanding from nothing. If that's true, then our universe might not be unique. It could be one bubble among countless others, each with its own physical laws and perhaps even its own version of time. In some, time could flow differently, faster, slower, or maybe not at all. In others, it could loop or branch. The multiverse, if it exists, may be the ultimate time machine, where every possible timeline plays out somewhere, somehow. When cosmologists run simulations of the early universe, they see the same thing again and again. In the beginning, everything is dense and hot, but as it expands, it cools. Structure forms. First hydrogen atoms, then stars, then galaxies, then the elements of life. And with each stage, entropy, the measure of disorder, increases. This increase is what gives time its direction. The arrow of time points from low entropy to high, from the simple to the complex, from the smooth fireball of the Big Bang to the textured universe we inhabit now. Without entropy, there would be no sense of past or future, no flow of moments. Everything would simply be. Some physicists think time is nothing more than our way of perceiving the growth of entropy, a psychological artifact of an expanding universe. And yet, deep inside the mathematics of quantum mechanics, time is curiously symmetric. The equations don't care which direction time flows. They work just as well backward as forward. That means the difference between the past and the future isn't written into the fundamental laws of physics. It's written into the conditions of the universe itself. This idea leads to a haunting possibility. If entropy could somehow be reversed, if the universe could begin to contract instead of expand, then the arrow of time might flip. The cosmos would run backward. Galaxies would shrink. Stars would unburn. Memories would unform. Every cause would become an effect, and every effect a cause. That brings us to a bold question. Could the universe ever collapse again? The same gravity that pulls things together might one day halt the expansion and pull everything inward. A big crunch, the mirror image of the Big Bang. Some models predict that the universe could oscillate, expand, collapse, and expand again in an eternal cycle, a cosmic heartbeat pulsing across infinite ages. If such cycles exist, each new expansion could be born from the ashes of the old, and perhaps each would carry faint imprints of its predecessor. In that sense, maybe the universe is already a time traveler, perpetually reborn from its own history. The Big Bang doesn't just mark the beginning of time. It's a hint that time may be a temporary phase, a property of this particular expansion. Beyond it, before it, after it, something timeless might exist. A quantum realm where cause and effect blur, where then and now dissolve into a single whole. Physicists call this the Planck epoch, when gravity and quantum mechanics merge. We can't describe it yet, but we can imagine it, a universe with no clocks, no space, no separation, only pure potential. And from that potential, time emerged, like a melody rising from silence. When you next glance at a clock, realize that every tick is part of that ancient rhythm, stretching back to the birth of everything. The seconds you count are threads in a cosmic tapestry woven over 8 billion years. Time isn't just something that passes, it's something that is. It's the shape of existence itself. So when we ask whether time travel is possible, we're really asking, can we bend that shape, fold it, twist it back upon itself? Can we step outside the melody and play it in reverse? In the next section, we'll explore what modern quantum theories say about that. From imaginary time to the astonishing idea that every moment might exist simultaneously, and time as we know it could be an illusion we create just to make sense of it all. Take a deep breath and imagine this. Every moment you've ever lived, every heartbeat, every thought, every decision still exists, frozen somewhere in the vast architecture of space-time. Past, present, and future aren't vanishing into nothingness. They're all laid out, side by side, like pages in an infinite book. You, right now, are simply reading one of those pages in sequence. This idea isn't poetic fantasy. It's one of the serious interpretations of Einstein's relativity. In his framework, time is woven into space to form a single four-dimensional fabric, space-time. Every event, the birth of a star, the fall of an apple, your next blink, occupies a definite coordinate within that fabric. From this perspective, nothing truly happens, everything simply is. We call this view the block universe, or the eternalist model of time. In a block universe, there is no universal now. Each observer's present is just a slice through space-time, moving according to their motion and perspective. What you call the future already exists. It's simply not yet reached by your consciousness. It's a humbling idea. It means that your entire life, past and future, may already be written into the geometry of the cosmos. You're just traveling along the timeline, experiencing each frame in sequence, the way a needle travels along a record. Now, if time is a dimension like space, could we, in principle, move through it the way we move through space? Could we walk from one moment to another? Quantum mechanics complicates this picture. At the smallest scales, time isn't smooth or continuous. It's jittery, probabilistic. In quantum theory, the future isn't fixed. It exists only as a range of possibilities, a cloud of potential outcomes waiting for measurement to collapse them into reality. This gives rise to another interpretation. Maybe the block universe isn't frozen, but branching. Every quantum decision, every particle spin, every uncertain event could cause the universe to split into parallel timelines. In one branch, you turn left. In another, you turn right. In one, the star goes supernova. In another, it fades quietly. In one, Earth thrives. In another, it never forms. This is the many worlds interpretation, and if it's true, then time travel might not change the past. It might simply move you into a different branch of reality. Imagine stepping into a time machine, traveling to the year 1900, and meeting your great-grandfather. According to many worlds, you wouldn't be altering your timeline. You'd be entering a parallel one, where your presence was always part of the story. No paradox, no contradiction. Just a new world added to the infinite branching tree of existence. But then comes an even stranger question. If all moments exist and all branches are real, what gives us the sensation of flowing through time? Why does it feel like the present moves? Neuroscientists think the answer lies in consciousness. The brain may act as a kind of temporal filter, integrating incoming sensory data into a coherent narrative we call now. We don't perceive time as it is. We perceive a smooth illusion constructed from discrete instants, much like a movie made from individual frames. In other words, the passage of time might not be an external reality, but an internal experience. Time doesn't flow, we do. That thought can feel liberating or unsettling. If time is an illusion, what does it mean to travel through it? What does it mean to change it? Perhaps time travel is less about moving through history and more about changing the frame of consciousness that perceives it. Still, physics isn't done with time yet. Some theories suggest that time itself might be emergent, a property that arises from deeper quantum processes. In certain models of quantum gravity, the universe at its most fundamental level has no time variable at all. It's described purely by relationships between things, geometry, fields, probabilities. Time appears only when large systems like us experience change. In that sense, time might be like temperature. On the microscopic level, atoms just move. Temperature only makes sense when you have enough of them interacting. Similarly, time might emerge only when enough quantum events interact in complex ways, the universe heating up into time. One of the boldest ideas comes from physicist Julian Barber, who argues that time doesn't exist, only change does. The universe is a vast collection of configurations, or nows, each one a snapshot of everything that exists. We experience motion because our minds remember other configurations, giving us the illusion of flow. But in reality, all possible moments exist together in a timeless landscape he calls Platonia. If Barber is right, then asking whether time travel is possible is like asking whether you can travel to a different part of a painting. You can focus on another area, shift your attention, but the whole picture already exists, so maybe, just maybe, time travel is already happening, not with machines or wormholes, but through awareness, the mind flickering between configurations of the universe, giving life its continuity and its mystery. Yet, physics doesn't live by philosophy alone. There are hard equations, experiments, and theories still trying to pin down time's secrets. From imaginary time in Hawking's cosmology to the deep symmetries of string theory, modern science continues to look for a bridge between quantum mechanics and general relativity, a theory of everything that can finally tell us what time is. And if we ever find that answer, it might turn out that we've been time travelers all along. Let's move from theory to experiment, from imagination to evidence. If time can bend, stretch, and slow down, then somewhere, somehow, we should be able to see it happen. And astonishingly, we already have. Einstein predicted it first. Time is not universal. It flows differently depending on your speed and your position in a gravitational field. The faster you move, the slower time runs. The closer you are to something massive, the more gravity stretches your seconds. This isn't metaphor, it's measurable. In 1971, physicists Joseph Hafele and Richard Keating boarded commercial airplanes with 4 atomic clocks. They flew once around the world eastward and once westward, comparing the clocks to identical ones left on the ground. When they returned, the airborne clocks disagreed with those on Earth by tiny amounts, just billionths of a second, but exactly what Einstein's equations predicted. That was the first time we saw time travel, not science fiction, but relativity in action. The pilots and passengers aboard those planes had literally moved through time at a different rate than everyone else on the planet. Since then, the precision has grown beyond imagination. Modern atomic clocks are so sensitive they can detect differences in elevation of mere centimeters. Raise one clock a few inches higher than another, and the higher one runs slightly faster because it's farther from Earth's gravitational pull. Time itself is stretching, right here in the room with you. You experience this every day without realizing it. At the top of a skyscraper, you're aging faster than someone at the ground floor. In orbit, astronauts aboard the International Space Station experience time more slowly than we do on Earth. When they return, they've traveled a fraction of a second into the future. It's subtle, almost imperceptible, but it's real. Every motion, every bit of gravity bends the river of time. The universe is a web of countless clocks, each ticking at its own rhythm, all woven together in the grand tapestry of space-time. Now imagine what happens near something far more massive, a black hole. The gravitational field is so strong that time itself nearly stops. To a distant observer, anything falling toward the event horizon seems to freeze, its final moment stretched forever. But from the falling object's own point of view, time flows normally. It crosses the horizon in seconds. This is more than just a thought experiment. In 2014, when scientists analyzed light from stars orbiting the supermassive black hole at the center of our galaxy, they observed redshift, light losing energy as time slowed near the immense gravity. It was direct proof that Einstein's predictions hold even at cosmic extremes. So, in a very real sense, we already have a form of time travel into the future. All you need is speed or gravity. But traveling backward, that's where the equations become strange and where possibility teeters on the edge of paradox. In the 1990s, physicist Kip Thorne, who later inspired the science behind Interstellar, explored the mathematics of traversable wormholes. Using the equations of general relativity, he found that under certain conditions, you could theoretically create a wormhole and move one mouth relative to the other. Say, accelerate one near the speed of light. Time dilation would cause the traveling mouth to age more slowly. When it returned, the two ends of the wormhole would be out of sync. step through one, and you'd emerge in the other at an earlier time. It sounds like a perfect time machine. But nature doesn't give gifts easily. To keep the wormhole stable, you'd need negative energy. Not just less than zero, but sustained, controllable, and vast. The only known form of it exists in fleeting quantum effects, like the Casimir effect, where tiny fluctuations in the vacuum create brief pockets of negative pressure between metal plates. For now, it's purely theoretical. But physicists have built tabletop experiments that mimic aspects of wormholes using electromagnetic fields or quantum circuits. Not true time machines, but analogues that help us understand the physics involved. And even without wormholes, other experiments have probed the strange interplay of time and quantum mechanics. In 2013, a team in Israel simulated quantum time travel using photons. They set up conditions mimicking what would happen if a particle went back in time and interacted with itself, and found that quantum mechanics allows self-consistent solutions. The past isn't rewritten, it adjusts. The math remains intact. This idea forms the heart of what's known as the Novikov self-consistency principle. The universe might allow closed time loops, but only ones that don't create paradoxes. You could go back and cause the event that sent you there, but you could never undo it. Reality, in this view, is flexible but self-healing. And then there's the quantum eraser experiment, one of the strangest demonstrations of how observation affects time itself. When particles pass through a double slit, they form an interference pattern, unless you measure which slit they went through. But in the quantum eraser, you can decide whether to observe the path after the particle has already hit the detector, and somehow that retroactively determines what pattern appears. It's as if the present decision reaches backward and rewrites the past outcome. Does that mean information can travel backward in time? Not exactly. But it means the boundary between past and future isn't as rigid as we once thought. Quantum reality doesn't unfold in a straight line. It's a web of interdependent events where the act of observation stitches the timeline together. Each of these experiments brings us closer to understanding that time isn't an external stream we drift through. It's part of the structure of reality itself, responsive to energy, gravity, and even consciousness. So, when you sit under the stars tonight, remember, time is not constant. It bends around mountains, slows in orbit, ripples with light, and trembles under your heartbeat. Every moment is slightly different everywhere, and in those tiny differences, the seeds of true time travel may already exist. In the next section, we'll explore what happens if we push those differences to their extremes. What happens when time breaks, loops, or vanishes entirely? Let's step deeper now, past equations and experiments, into the heart of what makes time so mysterious: paradox. Paradox is what happens when our minds, built to think in straight lines, meet a universe that bends back on itself. It's the tension between logic and possibility. And nowhere does that tension feel sharper than in the question, what if you could go back and change the past? The most famous version is the grandfather paradox. Suppose you travel back in time and prevent your grandfather from meeting your grandmother. That would mean you were never born, which means you could never have gone back in time in the first place. The chain snaps, reality contradicts itself, and causality collapses. At first glance, this seems fatal to the idea of backward time travel. But the universe might not be as fragile as we think. Some physicists believe it could be self-consistent, that no matter what you do, reality will adjust so that paradoxes can't occur. Imagine you go back to stop an event, but your actions accidentally cause it instead. The universe closes the loop perfectly. You become part of the story you were trying to change. This is the Novikov self-consistency principle, and it transforms paradox from impossibility into inevitability. You can visit the past, but you can never alter it, because your visit was always part of what happened. It's like watching a movie you've seen before. You can shout at the screen, but the ending never changes. Still, other theories take a different route. They say every possible outcome exists in its own universe. You go back, change something, and instead of rewriting history, you split the timeline. Two realities now coexist, one where the event happened and one where it didn't. The paradox dissolves, replaced by endless branching worlds. That's the many worlds interpretation again. Time travel without contradiction. Every choice, every moment, a new branch. Somewhere, every version of you is living out a different story. But there's another kind of paradox, quieter, subtler, and perhaps closer to home. It doesn't happen in physics labs or wormhole equations. It happens in our minds. You felt it before, déjà vu, that eerie sense that you've been here before, that this moment has already happened. Neurologically, it's a glitch, a misfire between memory and perception. But emotionally, it feels like a ripple in time, a brief overlap of timelines where the past and present brush against each other. Dreams, too, often play with time. Hours can stretch or collapse in seconds. Entire lifetimes unfold and vanish between blinks. Some dreams seem to predict moments that haven't yet happened. Is it coincidence, pattern recognition, or a sign that consciousness isn't entirely bound by linear time? Modern neuroscience suggests that the brain doesn't experience time uniformly. In moments of danger, adrenaline slows perception, letting milliseconds stretch into eternity. In deep meditation, time can seem to stop altogether. Our sense of time's passage is elastic, shaped by emotion, attention, and awareness. That means that time travel, at least in the subjective sense, is something you already do. You revisit memories, project into the future, and loop through imagined moments. The mind moves freely where the body cannot. Some psychologists call this mental time travel, the ability to simulate the past and future within consciousness. It's what allows us to plan, to regret, to dream. It's why we can feel nostalgia for what's gone and anxiety for what's not yet real. The mind is a machine built to move through time. But what if consciousness isn't just inside time? What if it helps create it? Some physicists, like John Wheeler, proposed that reality itself might depend on observation, that the universe doesn't fully exist until it's observed. If that's true, then consciousness doesn't simply witness time, it participates in shaping it. Could that explain why so many paradoxes vanish in quantum theory? Maybe time's consistency arises not from equations, but from observation, from awareness enforcing coherence on a universe that otherwise has infinite possibilities. Think about that the next time you remember something vividly. In that instant, you are reactivating the same neural pathways that once fired in the past. To your brain, the event is happening again. Neurons replaying time. The line between memory and experience blurs, and for a fraction of a second, the past lives anew. And then there are those strange human moments that science still struggles to explain. Premonitions, synchronicities, the sense of being guided by something unseen. Skeptics call them coincidence, but for some, they feel like whispers from other timelines, echoes of events not yet written. Physics doesn't confirm them, but it doesn't entirely rule them out either. Quantum mechanics leaves room for uncertainty, for probability waves that stretch across time. And inside that uncertainty, the human imagination thrives. Maybe that's why time travel fascinates us so deeply. It's not just about machines or equations. It's about longing, the desire to revisit what we've lost, to undo what we regret, to meet who we once were or might become. It's the ultimate expression of love and curiosity, the wish to touch eternity, even for a moment. So when you watch a sunset, remember, the light reaching your eyes left the sun 8 minutes ago. You're seeing the past painted across the sky. When you gaze at a distant star, you're seeing centuries or millennia into history. The night sky isn't a view of the present. It's a time machine, open to anyone who looks up. In the next section, we'll follow those photons, tracing how light itself might hold the key to understanding time's deepest secret. The possibility that time isn't fundamental at all, but something that emerges from the flow of information across the universe. Close your eyes for a moment and imagine light, pure, endless light, streaming across the cosmos. It touches everything, defines everything, and in a very real way is everything. Light is not just illumination, it is the universe's messenger, carrying information from the past to the present. It tells us what was, and in doing so, it defines what is. Every photon that strikes your eye tonight began its journey ages ago. The light of the nearest star took years to reach you. The glow of a galaxy you see through a telescope began before humans learned to walk upright. Light is time in motion, a record written in waves, traveling faithfully through the darkness. Einstein showed us that light holds a special place in the universe. Nothing moves faster, and for light itself, time does not pass at all. From the perspective of a photon, if we can imagine such a perspective, its entire journey from emission to absorption happens instantaneously. The distance between star and eye, between creation and destruction, collapses into a single event. To light, there is no before or after, only now. This idea carries an almost spiritual weight. The very medium that allows us to perceive time, light, exists outside of it. That might be the universe. Quiet hint that time, as we experience it, isn't absolute. It's a local phenomenon, a side effect of moving slower than light. And if time emerges from motion and information, then maybe the key to time travel isn't mechanical at all, it's informational. Physicist John Archibald Wheeler, one of Einstein's last collaborators, proposed a daring idea, it from bit. He believed that all physical reality, particles, energy, even space-time, arises from information. The universe, in his view, isn't made of matter. It's made of answers to yes or no questions. Everything that exists is the result of cosmic computation. In such a universe, time is the sequence in which information is processed. Every change, every interaction, every exchange of light is a tiny step in the grand calculation that gives rise to existence. If that's true, then to travel in time would mean changing how information is accessed, reading an earlier line of the universal code, or jumping ahead in the program. The laws of physics may not allow that yet, but quantum mechanics hints that the universe's data is far richer and stranger than we thought. Consider quantum entanglement, the phenomenon where two particles share a state so perfectly that measuring one instantly determines the other, no matter how far apart they are. Einstein called it spooky action at a distance, but it's real. We've tested it again and again, and the results are unambiguous. Entangled particles behave as if distance, and maybe even time, don't exist between them. Some researchers have taken this further. Could entanglement allow information to travel not just across space, but across time? Experiments at the University of Toronto and the University of Science and Technology of China have shown entanglement in time, where two particles that never coexist become correlated. One particle is measured before the other even exists, and yet their properties are linked. The future measurement seems to affect the past state. To some, this sounds like science fiction. To others, it's a glimpse of a deeper truth. Maybe the universe doesn't distinguish between time directions. Maybe all moments are woven together in a single quantum fabric, and causality is just a local illusion. If that's the case, then time travel might not mean moving through time at all. It might mean learning to navigate this fabric, to manipulate information in ways that let the past and future communicate naturally. Theoretical physicists exploring quantum gravity suspect that space-time itself could be a holographic construct, a projection of information stored on the universe's boundary. In such a model, time might not flow continuously but emerge from the changing relationships between bits of data. Picture a movie reel. The film strip already contains every frame, past, present, and future, but the story appears to move only when light passes through it frame by frame. Our universe could be like that, a cosmic film illuminated by consciousness. In that case, information doesn't just move through time, it creates time. Every act of measurement, every quantum interaction is the universe updating itself, writing the next line of the story. So perhaps the real question isn't, can we travel through time? But can we edit the story? We may already be doing so in small ways through the act of observation and decision. Each time we choose, each time we measure, we collapse probabilities into reality. The universe responds, and a new present is born. It's subtle, but it suggests something profound. The flow of time could be a feedback loop between consciousness and the cosmos, between the observer and the observed. In that light, time travel isn't a mechanical process to be engineered. It's an awareness to be mastered. In the next section, we'll step into that awareness, exploring the possibility that time is not fundamental at all, but a byproduct of consciousness itself. What if time, as we know it, exists only because we are here to experience it? Take a deep breath, let your shoulders relax, feel the moment you're in right now, the rhythm of your own breath, the sound of your heartbeat, the quiet hum of the present. Now ask yourself this, where exactly is now? It seems obvious. It's this moment, right? The one you're experiencing. But here's the strange part. When neuroscientists try to locate that present inside the brain, they can't find it. There is no single instant that the mind can call now. What we experience as the present is actually a construction, a mental integration of sensory data delayed by fractions of a second. Light takes time to reach your eyes, sound takes time to reach your ears, and the brain itself takes time to process it all. By the time you feel this moment, it's already gone. You are always living slightly in the past, a few milliseconds behind reality, and yet it feels perfectly immediate. That illusion is one of consciousness's most extraordinary tricks. It creates the experience of time flowing, even if, from the universe's perspective, everything simply is. Modern physics tells us that past, present, and future all coexist within the structure of space-time. Einstein himself said, "The distinction between past, present, and future is only a stubbornly persistent illusion." If that's true, then time, the thing we take most for granted, isn't a river flowing forward. It's a landscape already laid out. And consciousness is the traveler, moving through it frame by frame, like reading pages of an already written book. But what if the traveler and the landscape aren't separate? What if consciousness and time are two sides of the same coin? Some physicists and philosophers believe that consciousness might generate the sense of time. Without awareness, there's no before or after. There's just existence, timeless, undivided. Time appears only when perception divides reality into moments, when the observer starts measuring change. Think about it. Even in physics, time is defined by change, by motion, vibration, or decay. Without change, there's no time to measure. And change itself is only recognized by an observer who notices it. So perhaps the flow of time is the result of the mind noticing difference, a continuous comparison between what was and what is. Consciousness creates the illusion of movement through an otherwise still universe. This isn't just philosophy. It's a perspective gaining attention in the world of theoretical physics. In quantum mechanics, the act of observation affects reality. A quantum system remains in a state of probability, a blur of possible outcomes, until it's measured. Only when an observer interacts with it does one reality crystallize. Some researchers, like physicist Carlo Rovelli, argue that time might emerge from relationships between events rather than existing as an independent entity. In this relational view, time isn't something that flows. It's a network of connections, a web of correlations that becomes meaningful only through interaction. Others, like Roger Penrose, have suggested that consciousness itself might arise from quantum processes, that the brain's microtubules could host quantum coherence, allowing awareness to link with the very fabric of reality. If that's true, consciousness might not just experience time, it might be a part of how time unfolds. You can think of it like music. The notes themselves are static on the page, but when played, They create rhythm, a sense of flow, of direction. Consciousness is the musician, bringing the silent score of space-time to life. And here's a thought that bends the mind even further. If consciousness is entangled with time, could altering our state of consciousness change how we experience it? Deep meditation, for instance, often slows down or even suspends the sense of time. Moments stretch, awareness deepens, and what felt like an hour might have been minutes, or the other way around. Psychedelic research shows something similar. Under certain conditions, the brain's timekeeping networks become disrupted, and people report stepping outside time entirely, seeing it as a vast landscape, or existing in multiple moments at once. These are subjective experiences, yes, but they hint at something profound. Our sense of time isn't fixed. It's flexible, fluid, and deeply tied to the structure of consciousness. Maybe the next frontier of time exploration won't come from machines or wormholes, but from the mind itself. What if, instead of building a time machine, we become one? If consciousness is truly fundamental, if awareness is woven into the quantum fabric, then by altering perception, we might be able to glimpse other layers of reality. Perhaps time travel begins not in the lab, but in awareness, in understanding how the observer shapes what is observed. So, is time travel physically possible? Maybe not in the way Hollywood imagines, with spinning dials and glowing portals, but in the deeper sense, where time is a construct of perception and physics, perhaps we're doing it constantly. When you dream, remember, imagine, or love, you're bending time. You're reaching backward and forward across moments that don't yet exist or no longer do, and in that instant, the boundaries blur. You become, in a small but beautiful way, a traveler through time. In the next section, we'll return from the abstract to the physical, exploring whether future technologies could ever bridge this gap between theory and experience. Could we one day build a machine that manipulates space-time itself? Or is time travel destined to remain an inner journey, bound to consciousness? Let's bring our focus back to the physical, to the tangible universe of equations, energy, and engineering. We've explored time as an illusion, as perception, as consciousness. But what if, even within the laws of physics, there really is a way to build a bridge through time? It begins, as so many things in modern physics do, with Einstein. His general theory of relativity doesn't just describe gravity as a force. It describes it as the curvature of space-time itself. Massive objects, planets, stars, black holes, bend the fabric of reality, and in doing so, they bend the paths that everything else follows, including light and time. If you could manipulate space-time, twist it, fold it, stretch it, you could, in theory, alter the flow of time itself. In 1935, Einstein and physicist Nathan Rosen proposed something extraordinary: the Einstein-Rosen bridge, what we now call a wormhole. A wormhole is a hypothetical tunnel connecting two points in space-time. Imagine folding a sheet of paper so that two distant points touch, then poking a hole through them. That shortcut, that tunnel, is a wormhole. Mathematically, such tunnels could exist. They're allowed by Einstein's equations, but here's the catch: they're unstable. The instant one forms, it collapses. Gravity crushes it faster than light could travel through. To keep a wormhole open, you'd need something exotic, negative energy, or exotic matter, with repulsive gravity that counteracts collapse. In the 1980s, theoretical physicist Kip Thorne, who later advised on the film Interstellar, explored this idea deeply. He showed that, if exotic matter exists, it might be possible to create a traversable wormhole. And, astonishingly, by moving one mouth of the wormhole near a strong gravitational field, like near a black hole, time inside would slow relative to the other mouth. That means, step through one end, and you could emerge at a different time. A wormhole could become a time machine. Of course, there are enormous problems. Negative energy is not something we can produce in large quantities. It's been glimpsed only in quantum effects, like the Casimir effect, where two metal plates in a vacuum experience a tiny attractive force due to quantum fluctuations. But scaling that up to cosmic levels? Not yet, not close. Still, the equations don't forbid it. That's the crucial part. Another idea comes from closed, time-like curves, solutions to Einstein's equations that allow for loops in time. In such a spacetime, an object could follow a path that returns to its own past. The physics is consistent, but it raises all kinds of paradoxes. In 1991, physicist David Deutsch proposed a quantum version of these loops. In his model, paradoxes are resolved because the universe allows for self-consistent histories. Quantum systems entering a time loop interact with their past selves in a way that preserves consistency. In other words, you can meet your past self, but whatever happens between you was always part of history. These ideas sound theoretical, and they are, but they push the boundaries of what's mathematically possible. They tell us that time travel, though wildly impractical, is not strictly forbidden by physics. And then, of course, there are black holes, the most extreme objects in the universe, where space-time bends so sharply that not even light can escape. According to general relativity, time slows dramatically near the event horizon. To an outside observer, it almost stops. This means that, in principle, if you could orbit close enough to a black hole, without falling in, and then return to a distant region of space, you'd have effectively traveled into the future. Your clock would have ticked slower than everyone else's. This isn't science fiction. It's called gravitational time dilation, and it's been confirmed experimentally. Astronauts on the International Space Station age just a tiny bit slower than we do on Earth. Microseconds, but measurable. Near a black hole, that effect becomes enormous. In a sense, the universe already contains natural time machines. We just don't yet have the technology to approach them safely. Some scientists have proposed using rotating black holes, known as Kerr black holes, which may contain pathways to other regions of spacetime. The mathematics suggest such structures could exist, but they're likely unstable, destroyed by the slightest disturbance. Still, their existence in theory keeps the door open. And what about quantum teleportation? It doesn't move matter through space or time, but it does transmit quantum information instantaneously between entangled particles. This phenomenon doesn't allow faster-than-light communication, but it hints at deeper principles. That information, not matter, might be what truly moves through the universe. If one day we discover a way to manipulate information across time, as we do across space, perhaps teleportation will evolve into something even more profound: temporal communication. Could we send a message to the past? Could we receive one from the future? We don't know yet. But if the universe allows even one of these pathways, if the equations that describe reality permit it, then the question becomes not if, but how. Technology, after all, often catches up to imagination. Airplanes, rockets, quantum computers, all were once science fiction. So maybe, centuries from now, humanity will learn not to conquer time, but to collaborate with it, to navigate the folds of space-time with understanding, not force. For now, the best we can do is dream, calculate, and look up. Because each night sky is a living record of time's architecture, light billions of years old crossing cosmic distances to whisper stories of the past. And when you gaze at those stars, you are looking through a natural time machine, one that requires no exotic matter, no wormholes, no paradoxes. Just curiosity. In the next section, we'll journey even deeper, exploring how the arrow of time works, why time moves in one direction, and whether that arrow could ever be reversed. Let's pause for a moment and ask one of the most profound questions in physics, maybe in all of human thought. Why does time move forward? We take it for granted. We grow older, we remember the past but not the future, and we watch cause come before effect. Every cup that falls shatters, every fire burns out, every life begins and ends. But the laws of physics, the deep equations that govern the universe, don't actually require this direction. At the microscopic level, time is symmetric. If you film two atoms colliding and play it backward, the math still works. The equations of quantum mechanics, of electromagnetism, even of gravity, all remain perfectly valid in reverse. So why then does the universe have an arrow of time? Why is the past different from the future? The answer lies in one simple, powerful concept: entropy. Entropy is a measure of disorder, of how mixed up or spread out energy becomes over time. It's the heart of the second law of thermodynamics, which states that in any closed system, entropy tends to increase. That's why ice melts, smoke disperses, and stars eventually burn out. The universe moves from order to chaos, from low entropy to high, and that increase in entropy is what gives time its direction. It's not that time flows forward, it's that entropy grows forward. Imagine you drop a glass onto the floor. It shatters into 100 pieces. You never see the reverse, fragments leaping together to form a perfect cup again. Both are technically possible, but one is vastly more probable. The universe, it seems, always rolls downhill in probability. That's the thermodynamic arrow of time, the statistical push from order to disorder. But here's where it gets fascinating. At the moment of the Big Bang, the universe had extremely low entropy. Everything was smooth, ordered, compact, like a cosmic seed. From that improbable state, entropy began to increase, and the arrow of time began to tick. So time's direction, the reason we can't unburn wood or unage a body, may trace back to the initial conditions of the universe itself. Physicist Sean Carroll once said, "The arrow of time is a clue to the origin of the universe." He meant that understanding why entropy started low could reveal something fundamental about reality, maybe even why time exists at all. But why did entropy begin low? That's still a mystery. Some theories suggest the early universe wasn't as uniform as it seems, that quantum fluctuations created slight imbalances, giving entropy somewhere to grow. Others propose that our universe is just one side of a larger structure, that on the other side of the Big Bang, time flows in the opposite direction. Picture two universes expanding away from a single point of creation, each with its own arrow of time. From our perspective, one flows forward, the other backward. But from the universe's perspective, both are valid, two reflections in the mirror of existence. It's a breathtaking idea that what we call the future in our universe could be someone else's past in another. And even more astonishing, entropy doesn't just shape time, it shapes memory, perception, and life itself. Our brains, for instance, are entropy engines. Every memory we form, every thought we think requires energy, a conversion of order into disorder. We remember the past because the past left traces, physical imprints of lower entropy states that persist in the higher entropy present. You can't remember the future because it hasn't yet created those traces. The arrow of time in physics becomes the arrow of experience in consciousness. Entropy even governs the fate of stars and galaxies. Over billions of years, energy will spread thinner and thinner until the universe reaches heat death, a state of maximum entropy where no work can be done, no structure remains, no change occurs. Time, in a sense, would stop meaning anything. It sounds bleak, but maybe it's not the end. Maybe it's transformation. Some cosmologists speculate that once the universe reaches that flat, quiet state, quantum fluctuations could spark new beginnings, new Big Bangs, new arrows of time branching from the ashes of the old. Entropy isn't destruction. It's creation through change. It's the engine of evolution, the pulse of cosmic renewal. And in that endless cycle, time may not be a straight line at all. It could be a spiral, collapsing, expanding, collapsing again, a heartbeat of eternity. So when you think about the arrow of time, remember, it's not an enemy. It's what allows stars to shine, memories to form, and stories to unfold. Without entropy, there would be no motion, no life, no experience, just a frozen, perfect stillness. Time, as we know it, is the sound of the universe breathing. In the next section, we'll turn our gaze to the ultimate question. If the universe began in low entropy, could it ever reverse? Could time itself one day run backward? And what would that mean for existence, for memory, and for us? Close your eyes and imagine the end of everything. Not in a catastrophic, fiery explosion, but in silence. Stars fade, galaxies drift apart, and the universe cools into stillness. The cosmic background light dims until even its faint glow disappears into black. Time itself begins to lose meaning. This is the heat death, the far, far future predicted by thermodynamics. Every process has finished, every difference in temperature equalized. Entropy has reached its maximum. Nothing more can happen. But is that truly the end? Or could that silence be the beginning of something new? A reversal, a cosmic inhale after the long exhale of creation. Some physicists think it's possible. They imagine a universe that doesn't just expand forever, but one that might one day stop expanding, then begin to collapse back in on itself. A universe that rewinds its own story. This is known as the Big Crunch. In this scenario, the expansion of the universe slows as gravity gradually overcomes dark energy. Galaxies begin to move closer again. Stars, nebulae, and black holes start merging. Space contracts, temperatures rise, matter becomes denser. The universe that once stretched outward now folds inward. And as it does, something extraordinary could happen. The arrow of time might begin to reverse. Entropy, which has always increased, could start to decrease. Systems could become more ordered instead of less. The shattered glass reassembles. The smoke flows back into the flame. But would that mean time is actually running backward? Or would conscious beings, still bound to their own perceptions, simply experience the collapse as another version of forward motion, unaware that the universe itself is retracing its steps? Physicists like Sir Roger Penrose have proposed that perhaps the Big Crunch isn't the opposite of the Big Bang at all, but rather its continuation, that the end of one universe becomes the beginning of the next. He calls this idea conformal cyclic cosmology, the notion that, after heat death, the universe smooths out so completely that it becomes indistinguishable from the incredibly low entropy beginning of a new cosmos. In Penrose's model, the far future and the ancient past are connected. The death of one eon becomes the birth of another. Time doesn't end or reverse, it resets. Each cosmic cycle gives rise to new structures, new physics, new possibilities. It's an elegant thought that the universe might be immortal, not through stasis, but through rebirth. But there's another layer to this, a more philosophical one. If time truly reversed, would consciousness reverse too? Would memory run backward, thoughts unwinding in reverse order, our lives replaying from death to birth? It's hard to say. Our brains and every process within them depend on entropy. The act of remembering increases entropy. So if entropy reversed, memory itself might dissolve. You wouldn't notice time running backward, because your awareness would reverse along with it. From your perspective, everything would still feel normal. That's the strange beauty of it. Even if the cosmos were to play its movie in reverse, we would still be inside the story, experiencing it as forward motion. But maybe the Big Crunch won't happen at all. Observations suggest the universe's expansion is actually accelerating, driven by something mysterious, dark energy. This invisible force seems to push galaxies apart faster and faster, stretching space-time itself. If it continues indefinitely, the universe won't collapse. It will keep expanding until everything is so far apart that even atoms can't hold together. That end is called the Big Freeze, or sometimes the Big Rip. In the Big Rip scenario, dark energy grows stronger over time, tearing galaxies, stars, planets, even molecules apart. The very fabric of space unravels. No reversal, no renewal, just infinite expansion into nothing. It's a haunting vision. But there's also a quiet poetry in it, a reminder that even the universe, vast and powerful, obeys its own limits. Yet, despite these grim possibilities, there are hints that reality may be more complex. Quantum mechanics doesn't treat time as a simple arrow. In the quantum realm, particles can evolve both forward and backward in time. Some interpretations even suggest that events in the future could influence the past, subtly, probabilistically. In this sense, the universe may not need to collapse for time to reverse. Time might already be two-way. We just live in the part that flows one way. If that's true, then perhaps what we call the beginning and the end are illusions born of our limited perception, two edges of a much larger, timeless reality. And maybe, just maybe, consciousness itself exists outside that flow, observing the whole symphony at once. So whether the universe ends in a freeze, a crunch, or something beyond imagination, it might not be destruction at all. It might be rhythm, the rise and fall of a cosmic heartbeat. In the next section, we'll turn to a more personal question. If time travel were ever possible, what would it mean for humanity? Would we rewrite history, relive the past, or lose what makes the present sacred? Because beyond the equations and theories, time travel isn't just about physics, it's about meaning. Let's step away from the stars for a moment and turn inward, because time travel, for all its equations and paradoxes, is ultimately a question about us. If it ever became possible, if humanity truly learned to move through time, what would we do with that power? Would we fix our mistakes? Would we save those we've lost? Would we dare to change the past, knowing it might reshape everything that followed? The dream of time travel isn't just scientific, it's emotional. It's born from longing, the ache to hold on to what slips away, the hope of a second chance. We've all felt it, haven't we? That moment when you think, if only I could go back, to say something different, to choose another path, to stop the fall before it happens. But physics, and perhaps wisdom, tells us something humbling. The past, as far as we know, can't be undone. And maybe that's not a flaw in the universe. Maybe it's protection. If time could be rewritten, meaning itself might collapse. Every joy, every loss, every lesson learned would lose its weight, because nothing would truly endure. The permanence of time gives life its value. In a universe where everything is reversible, nothing really matters. But in a universe where moments pass only once, where every second is unique and unrepeatable, meaning becomes infinite. Even so, let's imagine just for a moment that time travel were possible. What would it do to society, to history, to identity? Think about this. If someone from the future traveled back and changed a small event, nudged a conversation, moved a stone, saved a life, it could ripple outward through time like waves in a pond. Entire generations could vanish or be rewritten. Wars might be avoided or never fought, but every gain might come with an unseen cost. The ethics of time travel are staggering. If you change one tragedy, do you erase someone else's miracle? If you prevent pain, do you also erase the strength it created? Philosophers call this the butterfly effect, the idea that a single, tiny action can cascade through complex systems and alter the future in unpredictable ways. It's not just poetic, it's grounded in chaos theory. In a non-linear system, like weather or history, even the smallest change can lead to massive unintended consequences. So even if time travel were possible, controlling it might be impossible. Reality could unravel faster than we could comprehend. And yet, maybe that's exactly why it's so fascinating. Time travel isn't really about changing the past. It's about understanding it. It's about looking at our own story with compassion and awe, realizing that every thread, even the painful ones, is woven into the greater fabric of who we are. Imagine if we could observe the past without altering it, just watch it unfold. To witness the birth of the earth, the rise of civilizations, the spark of fire in ancient hands. To see ourselves evolve, not as isolated beings but as part of a continuum stretching billions of years. Such a journey wouldn't just change our understanding of time. It would change our understanding of ourselves. we might realize that time travel, in a deeper sense, isn't about machines at all. It's about memory, empathy, and connection. When we remember someone we've lost, we're traveling to a moment that still exists within us. When we tell a story, we resurrect a piece of the past. When we imagine the future, we shape the path toward it. Every act of love, creativity, or forgiveness is, in its own way, a kind of time travel, rippling backward and forward through the hearts and minds of others. Maybe that's the real lesson. We don't need to escape time to transcend it. We do it every day, through thought, art, and understanding. And perhaps that's why the universe feels so mysterious, yet so intimate. Because time isn't something happening to us. It's something happening through us. We are the instruments playing its music. So, if time travel ever becomes possible, maybe the question won't be, can we do it? But should we? Would altering what came before make us wiser? Or would it strip away the lessons that made us human? Because sometimes, the greatest wisdom isn't in rewriting the past. It's in learning how to live fully in the present. And in a universe that might one day end, or reverse, or begin again, that's the most extraordinary kind of time travel there is. Ibrika, to be fully awake, right now, in this fleeting, beautiful moment of existence. In the next section, we'll explore how the philosophy of time travel has influenced culture and science itself, from ancient myths and Einstein's equations to modern film and artificial intelligence, and what these stories reveal about humanity's deepest desire to understand what time really is. Time travel has lived in our imagination far longer than it's lived in our science. Before Einstein, before relativity, before space-time was even a concept, humans were already dreaming of escaping the river of time. Every culture, every civilization has told stories about it. In ancient Hindu texts, gods could visit different realms where time flowed at different speeds. What felt like a few moments for them could be centuries for humans on Earth. In Greek mythology, the god Kronos personified time itself, devouring his children, symbolizing how time consumes everything it creates. And in the Bible, there are whispers of prophets transported through visions of the past and future, glimpses into the eternal. Long before science fiction, there was spiritual time travel, the belief that consciousness could move beyond the body, beyond the moment, to witness other ages. Then came the modern age, when imagination met mathematics. In 1895, H.G. Wells published The Time Machine, one of the first true science fiction novels. It wasn't just fantasy, it was a philosophical experiment. Wells' traveler builds a machine to visit the far future, witnessing the evolution and eventual decay of humanity. The story wasn't about technology, it was about perspective, the terrifying beauty of seeing time not as a series of days, but as an ocean. That single idea, a human being stepping outside of time, changed everything. Wells's story inspired generations of thinkers, from physicists to filmmakers. Even Einstein admired the imaginative courage it took to picture time as something one could travel through. And soon, science began catching up. Einstein's theory of special relativity revealed that time isn't absolute. It can stretch, bend, and even slow down depending on your speed. A clock on a fast-moving spaceship ticks slower than one on Earth. For the traveler, time passes normally. But for those watching from afar, they've leapt forward into the future. It's not fantasy. It's been tested. Astronauts aboard the International Space Station have technically experienced this, aging ever so slightly slower than those of us on the ground. That's not just poetic. That's physics. Then came general relativity, showing that gravity also warps time. The closer you are to a massive object, like a planet or a black hole, the slower your time flows compared to someone far away. This means time travel to the future isn't just possible. It's happening all the time, just in tiny, almost invisible amounts. But science fiction took these kernels of truth and turned them into universes. Movies like Interstellar made us feel the heartbreak of time dilation. A father aging hours while his daughter ages decades. Back to the Future turned physics into adventure. And Tenet showed us a world where time itself becomes a battlefield. Bullets flying backward, explosions imploding. Why are we so obsessed with this idea? Because time travel is the ultimate form of freedom. It's the power to escape fate, to transcend the one law that governs everything: impermanence. Every time we watch a time travel story, we're not just chasing science fiction, we're confronting our own mortality. We're asking, can we ever truly lose something? Or does every moment, every life, continue to exist somewhere, eternally preserved in the folds of space-time? Einstein once said, "After the death of his friend Michel Besso, Erbruchi, he has departed from this strange world a little ahead of me." That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. To Einstein, all moments in time exist simultaneously, like pages in a cosmic book. We experience them one by one, but the book itself is already written. Every laugh, every goodbye, every sunrise. It's all still there, somewhere in the vast geometry of space-time. This idea, known as the block universe, is one of the most profound consequences of relativity. It means that the universe doesn't flow. It is. Past, present, and future all coexist. Time doesn't pass, we do. And if that's true, then time travel might not be about moving through time, but shifting perspective. Like walking from one page to another in the story of existence. Quantum mechanics adds another twist. At the quantum level, the boundaries between past and future blur. Particles can interfere with their own histories. Some interpretations, like the transactional interpretation, even suggest that quantum events involve waves moving both forward and backward in time, meeting in the present to create reality. In this view, the universe is constantly negotiating between what was and what will be. Reality isn't fixed. It's a dialogue between directions of time. So perhaps our obsession with time travel is more than fantasy. Maybe it's intuition, a deep subconscious recognition that time isn't as rigid as it seems, that in some profound way, we are already time travelers. Through memory, imagination, and quantum possibility, we cross timelines every day. We live in yesterday's dreams and tomorrow's fears, in the ghost of what's gone and the echo of what's coming. And if the universe truly contains all moments forever, then perhaps we never really leave any of them behind. We just turn the page. In the next section, we'll explore how modern physics and artificial intelligence are working together to simulate and perhaps one day recreate the flow of time itself. Could an AI learn to predict the past as easily as it forecasts the future? And what would that mean for our understanding of time, memory, and destiny? Picture this: a supercomputer humming quietly in a darkened lab, its processors glowing faintly like neurons in a vast digital brain. Lines of code flow through it, not just to predict the weather or the stock market or a chess game, but to simulate reality itself. Now imagine that somewhere within that simulation, time unfolds. Moments tick by, events occur, decisions are made. From the inside, it feels real. But here's the question: what if the universe itself works the same way? What if time isn't a fundamental feature of reality, but an emergent illusion born from computation, from the processing of information? This is where quantum mechanics meets artificial intelligence, and the boundary between physics and philosophy begins to dissolve. AI systems today can do something astonishing. They can predict frames of video before they happen. They learn the rules of cause and effect from vast datasets, generating what the next moment should look like. In a way, that's a form of time simulation. But here's the twist: some physicists suggest that this might not just be a metaphor. The universe itself could be doing something similar, computing the next frame of existence based on the rules of quantum mechanics and the information of the present moment. Every atom, every photon, every fluctuation of energy could be part of an unimaginably vast quantum computation, a cosmic program running across space-time. And if that's true, then time, as we experience it, might just be the rhythm of that computation. The universe updating itself, frame by frame. This idea echoes what thinkers like John Wheeler proposed, it from bit, the notion that every particle, every field, every event ultimately arises from information. Reality, in this view, is not made of matter, but of meaning, encoded in the language of the cosmos. Now, let's connect this to AI again. Modern AI doesn't just predict, it learns patterns that humans can't even see. It can find hidden structures in chaos. It can recognize subtle relationships between events across time. In a strange way, AI is beginning to mimic the predictive power of the universe itself. Some researchers have suggested that if an AI could process enough quantum data, it might be able to reconstruct parts of the past or simulate branches of the future, not by magic, but by pure probability, following the same rules that particles do. Imagine that, a machine capable of seeing both directions of time, one that could model not just what will happen, but what might have happened if reality had made slightly different choices. Would that make it a kind of time traveler? A digital oracle glimpsing across timelines? Maybe. But it would also force us to confront a deeper question. If a simulation of time is indistinguishable from time itself, does it matter which is which? Consider simulation theory, the controversial idea that our universe might itself be a vast computational construct. If true, it wouldn't mean we're fake. It would mean that reality operates by rules so precise, so consistent, that consciousness can emerge within them, just as characters can emerge inside a perfectly rendered story. And what is time inside a simulation? A loop of instructions, a sequence of updates, an evolving state of information. In this sense, both AI and the cosmos are storytellers. Each computes reality one moment at a time, guided by rules, but open to infinite variation. Some scientists have begun experimenting with quantum neural networks, systems that use quantum bits to learn, think, and adapt. These machines don't just process data in one direction. They can, in principle, operate across superpositions, exploring multiple timelines simultaneously. That means, in theory, a quantum AI could glimpse multiple possible futures at once. It wouldn't see time as linear. It would experience it as a field of probabilities. If humans ever build such a system, one capable of perceiving time not as a flow, but as a landscape, we might finally understand what time really is. Because right now, we only ever experience one thread, one version of events, one continuous now. But the deeper we look, into quantum mechanics, into computation, into the architecture of consciousness, the more it seems that time is not a river, it's an ocean. Every possibility, every moment, every choice exists simultaneously, overlapping like waves. We just sail one current at a time, guided by perception, and maybe by something deeper than physics, awareness. If AI can learn to simulate time, to model both the past and the future, then perhaps the next great question won't be, can we travel through time? But can we understand it? Because understanding is a kind of mastery. Not control over the clock, but harmony with it. And if consciousness and computation are reflections of the same universal process, then maybe, just maybe, awareness itself is the universe's way of experiencing its own time. So perhaps the first true time traveler won't be a human stepping into a machine, but an intelligence, born from both silicon and mathematics, perceiving all of time at once. And that brings us to our next journey, section 19, where we'll explore the deepest paradox of all, If time is an illusion, what does that make us? Are we travelers through time or patterns within it? And if everything that ever was and ever will be already exists, what does it mean to be alive right now? Take a deep breath. Feel the air move in and out of your lungs. For just a moment, forget the stars, the theories, the equations, and turn your attention inward, because everything we've explored, relativity, quantum mechanics, time dilation, cosmic expansion, all of it ultimately leads to one question. If time is not what it seems, then what are we? We experience life as a story, unfolding one moment after another. But if the universe is a timeless block where past, present, and future all coexist, then perhaps now is just the slice of reality our consciousness happens to illuminate, like a flashlight moving slowly across a painting that's already complete. Each section lights up as we move, giving the illusion of motion, of flow. But the whole masterpiece already exists. Could it be that consciousness is not inside time, but that time is inside consciousness? Quantum mechanics hints at something extraordinary, that observation doesn't just reveal reality, it creates it. The act of measurement collapses possibilities into a single event. Without observation, the universe remains in superposition, undefined, potential, waiting. In that sense, every conscious being is a participant in the unfolding of the cosmos. We're not separate from the universe, we're how the universe knows itself. Einstein once wrote, "The distinction between past, present, and future is only a stubbornly persistent illusion. But to us, that illusion is everything. It's where love happens. It's where stories unfold. It's where meaning is born. And maybe that's the point. Maybe the universe needs the illusion of time to experience itself, to feel, to evolve, to reflect. Think about it. If all moments already exist, then birth, death, joy, and sorrow all coexist in the eternal structure of reality. Yet here we are, moving through it, feeling each second as it arrives. We are time travelers, not in the physical sense, but in the experiential one. The arrow of time moves through us, and in doing so gives rise to the miracle of experience. But who exactly is the traveler? Who is it that witnesses time moving forward? Neuroscience tells us that consciousness is a process, an emergent property of billions of neurons firing in patterns. But those patterns are themselves governed by physics, by time, and yet, somehow, we can reflect on time. We can remember, anticipate, imagine. The brain may operate within time, but awareness observes it. This raises one of the most profound questions ever asked. Is consciousness an emergent feature of time, or is time an emergent feature of consciousness? Some physicists and philosophers, from Schrödinger to David Bohm, believed that mind and matter are two sides of the same reality, that consciousness and the physical universe arise together from something deeper, a timeless source beyond space and causality. If that's true, then maybe time isn't something we move through at all. Maybe it's something we project, like a film playing on the screen of awareness. Every thought, every heartbeat, every memory is a frame in that film, giving the illusion of sequence. But beyond the frames, beyond the real, lies the stillness of pure existence. Timeless, infinite, unchanging. Mystics across cultures have described similar insights. They called it enlightenment, awakening, transcendence, the direct realization that past and future dissolve into an eternal present. And now, modern physics may be approaching that same truth from the opposite direction, through mathematics instead of meditation. What if the two paths meet? What if science and spirituality are just different languages describing the same reality, one that is ultimately timeless? In such a universe, we are not in time, we are time. We are the unfolding, the awareness, the motion itself. Each of us a momentary expression of something infinite, consciousness experiencing itself as human for a little while. And maybe that's why time feels so personal, why we can feel nostalgia for moments long gone, or hope for ones not yet born, because deep down, we already contain them all. The past lives within our memory, the future lives within our imagination, and both of those live within the timeless space of awareness that is reading these words, right now. So perhaps the answer to whether time travel is possible isn't found in equations, but in experience. We travel through time every moment we breathe. We journey through memory, through anticipation, through the unfolding present. Each thought is a step, each heartbeat, a passage. And if the self, the consciousness behind your eyes, is not bound by time but merely observing its flow, then maybe, in the deepest sense, we have already transcended time. Maybe the ultimate journey isn't about escaping the timeline, but realizing that we are the timeline, and that the entire story of the universe is written within us. In the final section, we'll bring everything together, science, imagination, and existence, to ask one final haunting question: are we? If time travel is possible, what destination could ever be more extraordinary than this one? This fleeting, precious, impossible moment we call now. So here we are. After all the equations, theories, and dreams, at the edge of everything we can understand. We began with the question, is time travel physically possible? And somewhere along the way, that question transformed. It became not just about science, but about what it means to exist at all. Because the deeper we explored, the clearer it became. Hebrew time is not simply a line stretching from past to future. It's a dimension woven into the very fabric of reality. Flexible, mysterious, alive. Einstein showed us that time bends with motion and gravity. Quantum physics revealed that, at the smallest scales, time may blur, dissolve, or even vanish altogether. Philosophy told us that what we call the present is just a boundary, the edge of our awareness touching infinity. And yet, through all that complexity, one truth remains simple and profound. This moment, right now, is the only place the universe truly meets itself. Maybe that's the real secret of time travel, not stepping into a machine or bending space-time, but awakening to the infinite depth of the present. Because think about it. The past only exists as memory, a reconstruction happening now. The future only exists as imagination, a projection unfolding now. And the present is the only frame where energy becomes experience, where possibility collapses into being. Everything that ever was and everything that ever will be converges in this single flicker of consciousness we call now. Look around you, wherever you are. The light falling on your hands left the sun about 8 minutes ago. The air you breathe carries atoms once exhaled by ancient stars. The thoughts in your mind are the latest notes in a symphony that began 13.8 billion years ago. You are not separate from time. You are time, condensed into awareness. You are the universe remembering itself. When we long to travel through time, what we're really longing for is understanding, to make peace with the flow, to see the pattern behind the passing moments. We ache to hold on to what is fleeting. But perhaps the beauty of existence lies in that very impermanence. Because if everything lasted forever, nothing would move. And if nothing moved, there would be no life, no love, no change, only stillness. Time, in all its mystery, is the universe's way of breathing. It gives rhythm to creation. It turns the static into the living. So maybe the question isn't, can we travel through time? Hebrew. Maybe it's, can we travel with it? Can we flow with its current without resistance, cherishing each second as it passes, knowing that within every loss, something new is being born? The physicist Brian Greene once said, "The past and future are as real as the present. We just happen to be in the now." And perhaps that's the greatest gift time gives us, the ability to be in it, to experience it, to feel the miracle of existing between what has been and what is yet to come. So, as our journey ends, take a deep breath, close your eyes, listen to the faint hum of existence, the pulse of your heart, the whisper of space expanding, the echo of ancient light still traveling through the cosmos. That's time speaking. That's the universe, alive, evolving, and you are part of its story. If one day someone does build a time machine and humanity learns to walk among the stars of yesterday and tomorrow, I hope they remember this moment, this quiet awareness, as the true destination. Because no matter how far we travel, no matter which era we visit or which galaxy we reach, we will always return here. Ibrahi to now. And maybe, just maybe, that's all the time travel we were ever meant to find. So if you've journeyed with me this far, thank you. If you felt wonder, curiosity, or calm, that's the real science of it. Because awareness itself is the greatest experiment the universe has ever run. If you enjoyed this exploration, don't forget to like, subscribe, and share. It helps more curious minds find their way to this quiet corner of the cosmos. Until next time, stay curious, stay timeless, and remember, Apri, the future is already here, waiting for you to arrive.